This is a proof that the sum from r equals 1 to n of r is equal to a half n plus 1, and I'm going to use induction. So firstly, letting n equal 1. Well, on the left hand side we have the sum from r equals 1 to 1 of r, which is 1. And on the right hand side we have a half times a 1 times 1 plus 1, which is also 1. So the left hand side is equal to the right hand side, which means that the formula is true for n equals 1. Okay, now we make our huge assumption. We assume that if we add up from 1 to k, where k is a specific fixed number, then we do indeed get a half k plus 1. So this is saying that the formula is true when n is k. What we want is to be able to show that if that's true, then this will also be true. The formula will also be true when n is k plus 1, which is a half k plus 1, k plus 2. That's what we're going for. Okay, let's do our inductive step. So we start with the thing that we want. We want to investigate r is 1 to k plus 1 of r. We go from 1 to k, and then we go from k plus 1, well, just to k plus 1, we just stay at k plus 1. So that's breaking that up, 1, 2, 3, k minus 1, k plus 1. It's breaking it up into 1 to k, and then k plus 1. Now we've made an assumption about 1 to k, which is that it's a half k plus 1. We made that up, but we assumed it's true. And the sum from k plus 1 to k plus 1 of r is simply k plus 1. Okay, I'm going to pull out a common factor of k plus 1, leaving me with a half k plus 1. And what we've got there, if I pull out a half, is k plus 1, k plus 2, which, if you look back there, is what I wanted as required. So if it's true for n equals 1, only if it's, if it's true for n is k, only if it's true for n is k. Don't forget, we totally made this up. And then we used it. Made it up here, and then used it here as if it was true. So our conclusion is only if it's true for n is k. But if it is true for n is k, then it will be true for n is k plus 1. And it's true for n is 1. So that gets the ball rolling. So therefore, it is true for all n greater than or equal to 1. Now let's prove that the sum from 1 to n of r squared is a sixth n plus 1 to n plus 1 by induction. When n is 1, the left hand side is the sum from 1 to 1 of 1 squared, which is 1 squared, which is 1. The right hand side is 1 sixth, 1 plus 1, 2 times 1 plus 1, which is 1 sixth of 2 times 3, which is 1. So the left hand side equals the right hand side when n is 1. So it's true for n is 1. Okay, let's make our assumption. We're going to assume that it's true when n is k. That if we go from 1 to k, then we will get a sixth k plus 1, 2k plus 1. Okay, what we want is that the formula will be true for k plus 1, meaning that if we went all the way to k plus 1, we would get a sixth k plus 1, k plus 1 plus 1, 2k plus 1 plus 1, which is 1 sixth k plus 1, k plus 2, 2k plus 3. Okay, let's see if we can get that. So we start investigating what we want. R is going from 1 to k plus 1, and we're going to split that into the first k and then the final k plus 1. Oh, forgot my squared on the r. Oh, I forgot it everywhere, look. I wonder if you noticed that. Squares all over the place went missing. Okay, so we've made the assumption that the sum from 1 to k of r squared is thick k plus 1, 2k plus 1. And then the final term here, when r is k plus 1, we get k plus 1 squared. We're stopping when r is k plus 1, so that's the only term. Okay, let's pull out a common factor of k plus 1. So we get 1/6 k, 2k plus 1, plus k plus 1. And I'm going to pull out a sixth as well. Oops. Sixth, k plus 1. And then in here I've got k, 2k plus 1, plus 6k plus 6, which hopefully is going to tidy up nicely. Let's have a look. We've got 2k squared plus k plus 6k is plus 7k plus 6, which factorises to, what does it factorise to? 2k plus 3 and k plus 2. Does it? Is that true? Yes, it is. Good. Right, so that is as required, because you can see that it's the same as I wrote down as what I wanted up here. And what have I shown? I have shown that if it is true for n is k, if, then it will be true for n is k plus 1. And to get the ball rolling, it's true for n is 1, therefore, in one little domino step, it is true for all n greater than or equal to 1. One more. Okay, let's prove that the sum from 1 to n of r cubed is given by a quarter n squared n plus 1 squared. We'll check n is 1 first. The left-hand side gives us 1 to 1 r cubed, which is 1 cubed, which is 1. The right-hand side gives us, it doesn't give us a sum at all. The right-hand side gives us 1 quarter times 1 squared times 1 plus 1 squared, which is 1 quarter times 4, which is 1. So the left-hand side equals the right-hand side, so it's true for n is 1. Okay, let's write down our assumption. We're going to assume that the statement is true if we go up to k. So that means that if we do the sum from 1 to k of r cubed, we get a quarter k squared k plus 1 squared. What do we want? We want the sum from 1 to k plus 1 of r cubed to equal 1 quarter k plus 1 squared k plus 1 plus 1 squared, which is 1 quarter k plus 1 squared k plus 2 squared. Okay, let's investigate. Start with what we want. We want to know what is going on when you go all the way up to k plus 1. Split it into two parts, 1 to k, and then k plus 1, well, just to k plus 1, because that's the end. We've made an assumption about the first bit. We've assumed, we made it up, but we have assumed that it's equal to a quarter k squared k plus 1 squared, and that final term when r is k plus 1 is just k plus 1 cubed. Let's pull out a common factor of k plus 1 squared, and I'm also going to pull out a quarter, leaving me with k squared plus 4k plus 1, which I think factorises k squared plus 4k plus 4 to 1 quarter k plus 1 squared k plus 2 squared as required when I wrote it down here. That's what I wanted. So I have proved that if it is true when n is k, if I make that completely made up assumption, then it would be true when n is k plus 1. And indeed, it is true when n is 1, and therefore it must be true for all n greater than or equal to 1.